you want to look at it, imagine that you've got the ground over here, and your constraint is a circle, right, on the ground. Well, it should be at the origin, sorry. And that comes up, and won't it punch through? That cylinder will punch through your surface. And what shape will that be on your surface? Well, hard to say, right? Hard to say. It's probably going to be like a wavy circle, right? If you looked at it from the top, wouldn't it look like a circle? Yeah. But it's probably some wavy circle. Yeah? And what we're trying to do is find the highest and lowest points on that wavy circle. So we have a function subject to a constraint. We're trying to find the highest and lowest points on there. That all kind of visually makes sense so far? That's just with my drawings. I've got better stuff. You'll see better stuff here in a moment. All right, so we've got this function. Surface function of two variables, subject to constraint. Our constraint equation has two variables in it and a constant. Then, how do we find the max and mins? Here's how. What we do to find the maximum and minimum values of f is this. Part A. We find all the values of x, y, and lambda. Lambda is just some number, some constant. All the values of x, y, and lambda that satisfy these two equations. First, you recognize that symbol? It's the gradient. You want to know what x, y, and lambda, what three values there, x, y, and lambda, will make the gradient of f equal to some scalar multiple of the gradient of g. What x, y, and lambda will make the gradient of f parallel, isn't the gradient a vector? Will make this vector, isn't a scalar multiple of a vector still parallel? So what we're saying is we want to know when the gradient of f is parallel to the gradient of g. When the gradient vector of the surface function is parallel to the gradient vector of our constraint surface, right? Wherever those two vectors are parallel, believe it or not, is where maximums and minimums occur. Explaining that is hard to explain, okay? It's really hard to explain why it's true, but it is. And then not only does that need to be true, the gradients have to be parallel, but of course the x, y, and lambda you use has to satisfy this equation. Like if you find an x and y that makes the top one true, but it doesn't make that true, then it doesn't work. You need to be, the x, y, and lambda have to satisfy both equations simultaneously. Once we figure out the x, y, and lambda that make these true, there might be more than one answer. We have to evaluate our original function at those points, and then we just look at them and say, oh, that's the biggest one, that's the smallest one, okay? And that's it. That's all we do. That's the procedure. So this is the same procedure written in different notation, right? What we need to do is we have to figure out where the gradients are parallel, right? What does that mean? Well, what is the gradient of this? Remember, the gradient meant the partial of f with respect to x is a vector, right? Partial of f with respect to x, partial of f with respect to y. That's what this is. Has to be equal to lambda times this gradient is the partials with respect to x and y respectively, and then just pass the lambda through. That's what the first condition really means, right? But two vectors can only be equal when? When their components are equal. So I have to set that component to that component, and set that component to that component. So at the end of the day, we have to satisfy three different things. The first thing is that these two components must match. That's the first equation. The second equation is that these two components must match. And then the third equation we have to solve is that the original constraint equation must be true. If we can satisfy those three equations simultaneously, then we will have found the x, y, and lambda where we have possible maxes and mins. So we're trying to solve a system of equations, right? This is a system of equations. Three of them. Three equations. How many unknowns? X, y, lambda. Three unknowns. Three equations, three unknowns. But they're nonlinear. So when you see me in class set this up, the way I'm going to do this is I'm going to write the first equation I'm trying to solve, then the second one, and then the third one. I'm going to put them kind of side by side like that. I'm going to try and see if I can solve all three equations, get a solution that works for all of them at the same time. All right, there it is. Find the maximum and minimum value of this surface, x squared plus 2y squared. There's the surface, right? So there's my surface right there. But I want to restrict the domain to the circle x squared plus y squared is 1. That means if I take this surface and I only restrict it to that domain on the ground, right? That's the domain on the ground. I want to restrict it. Only those points are allowed to be plugged in. If we map this into the surface, or if you look at it like a cylinder where it punches through, then you're going to get this curve, right, on that cylinder. Let's take the domain out of the ground there. Let's go ahead and just take the surface out as well. I did that nice and slow. All right, there we go, right? There's that blue curve. And what we want to do is see if it's possible to find those points right there. Right? It has max and it has a min. We need to figure out what the max is, what the min is, and if possible, where they occur. Right? Could we do what we did just a second ago with the boundary? Could we? Could we do the method we did in the previous? Could I just call the circle C1 and just go around the circle? Yes, but how would you deal with the fact that it's not a function? See what I'm saying? Like, wouldn't you have to break it into like different pieces? Like for part of it, you'd use the positive square root, and then the other part you use a negative. You could probably do it, but Lagrange is probably going to be much easier for this type of problem. By the way, and this is still a very simple problem with respect to Lagrange, so it's our first example. Let's just do it. Okay, I'm going to try Lagrange. Just to be clear, that's my function, right? I'm going to use Lagrange. This right here is my g of x, y. Okay, on the side here, I'm going to write the three equations just so we have them. What were the three equations that I must simultaneously solve? Equation 1. Equation 1 was that the partial of f with respect to x must equal lambda partial of g with respect to x. Equation 2, partial f with respect to y must equal lambda times partial g with respect to y. Equation 3, that g of x, y must be k. That just means that that constraint equation must always be true, all right?
What do we have to get for k?
K is 1 here.
Okay.
Do you see K is 1?
Yes.
Thank you for mentioning that. Yeah, we don't have to solve for K. K is going to be any constant. All we do to figure out what g of x, y is, make sure you get all your x, y's to one side of the equation. And then any number that's left on the other side, you could call K. Okay? Okay. Yeah. All right. Let's do it. Equation 1. Okay, equation 1. All right, what is the partial of f with respect to x? I'm going to write here what I'm doing. 2x. 2x must equal, okay, lambda I don't know, right? What's the partial of g with respect to x? 2x. Well, that's not so bad. Okay, next equation. Equation 2, I'll solve that in a second. Equation 2, I need the partial of f with respect to y equals lambda partial g with respect to y. Partial of f with respect to y is 4y. Must equal lambda times partial of g with respect to y, 2y. Hey, that doesn't look too bad, does it? Equation 3 is x squared plus y squared must be 1. Okay. I've just got to figure out all the values of x, y, and lambda, all of them. I have to consider every one of them that make all three of those true at the same time. So let's go back to this first equation right here. I'm going to tell you what I'm not going to do. I'm not going to divide both sides by x, right? Because if you divide both sides by x here, then you eliminate the possibility that x could possibly be 0, right? And can x be 0? Maybe. I don't know. So I don't ever want to divide by a variable unless I explicitly tell you, hey, look, I'm telling you x is not 0, now let me divide by 0. I'm going to avoid that by doing this. I'm going to move the lambda 2x to the other side of the equation by just subtracting it, right? And now I'm going to factor a GCF out of the left. You with me? Okay. What does that mean? Set both of them equal to 0. So what are my solutions? X is 0 or lambda is 1. X is 0 or lambda is 1. So just keep in mind what we've got going here. We must satisfy all three equations at the same time, right? And so far what we've said is to satisfy equation 1, you either have to let x be 0 or you have to let lambda be 1. All right? Let's go look at the second equation. We'll come back to that in a minute. For this one, I'm going to do the same thing. I'm going to pull the lambda 2y to the other side to make it equal 0. I'm going to pull a greatest common factor out of this. 2y leaves me with 2 minus lambda equals 0. And that means y must be 0 or lambda equals 2. All right. We're good? Now what I need to do, separate from these equations, I need to look at all these different scenarios. All right? All these scenarios. So now here's where you being very clear with what you're doing is going to be important. You have to be very clear in like where you are in the process. So the first thing I'm going to do is I'm going to say I want to suppose this is true first, all right? And the way I say suppose, the way mathematicians say suppose is like that. It's an S with a little line on the back of it like that. That means suppose. Suppose x is 0. Okay? Then do you agree that that means equation 1 is good? We've satisfied equation 1. All right. Now, with x being 0, does that have any impact on this? Like there are no x's here, right? Okay. How about x being 0 here? Well, if x is 0, then equation 3 now tells me what? 0 plus y squared equals 1, which means that y squared must be 1, which means y must be 1 or y must be negative 1, right? Plus or minus 1. So when x is 0, y has to be plus or minus 1. Yes? Now, that would satisfy what equation? If x is 0, equation 1 satisfied. Equation 3, y would have to be plus or minus 1, right? Which would mean that equation, 3 is satisfied? Right? Equation 3 is now satisfied? But what about equation 2? We need to satisfy equation 2. It says that y has to be 0, but what are we saying? Y is what? 1 or negative 1, right? So that's not true, which forces what? Lambda to have to be 2. So equation 2, we have to let lambda be 2. And now, if we do that, equation 2 is satisfied. Does that all kind of make sense to you? So let me see what I can conclude from this. I can conclude that if x is 0, y could be, ooh, I don't know why I did a big old comma like that. If x is 0, y can be 1, and then lambda would have to be 2, right? I'm going to write it as like an ordered triple, x, y, lambda. And then, or you could do what? 0, you could have negative 1, then you could have 2, right? This right here, these three values, don't look at this as like x, y, z. This is just, remember, for Lagrange, we need to find an x, a y, and a lambda that make all three true at the same time. They're the x, y, and lambda. Right? Okay. Are we done?
No.
No, because all of this was just living under the suppose, what, x is 0. Now what I need to do is, I can go and say what happens when lambda is 1 now. Okay? Let's do that now. This gets exhausting because you're like not sure when you're done. You have to cover everything, all the cases, or else you'll miss something. So I'm going to put on the side here so far what we've got. We've got 0, 1, 2. We've got 0, negative 1, 2. And remember, this is x, y, and lambda. All right, now we're moving on, keeping this up here. Let's suppose now you want lambda. You don't have to go in any particular order. Okay, so if you wanted to right now, you could suppose y is 0. It's up to you. I'm going to just go in the order. Suppose lambda is 1. If lambda is 1, what? Equation 1 is good? Okay. If lambda is 1, that has no impact on this, does it? But what about lambda being 1 here? Yeah, well, if lambda is 1, what happens? We can go to any of these. Which one? Here? You want to go here? It doesn't. I don't care. Let's go here, right here. Okay? So if lambda is 1, then equation 2 becomes 4y equals 2y. Solve for y. Subtract 2y on both sides. 2y equals 0. That means y is 0. So if lambda is 1, equation 1 is satisfied, right? And it forces equation 2 to give you a y equals 0, right? Which actually satisfies equation 2. Because doesn't equation 2 require y to be 0? So this right here makes equation 2 true. And now we need to look at equation 3. Equation 3 we haven't dealt with, right? So far equation 1's good, equation 2 is good. How do we get equation 3? Well, equation 3, what does it become? Well, what do we have? Y is 0, right? Remember, we're living all under this supposition that this lambda was 1, which forced y to be 0, which if y is 0, that forces this to become x squared plus 0 squared equals 1, which means x is 1 or x is negative 1, right? And now equation 3 is good. So I've got equation 1, 2, and 3 are all good. So let's see, what do my triples look like here? 1 for x, what was y? 0, and then lambda was 1. Or I could have negative 1 for x, y was 0, and lambda was 1. Okay, so I'm going to put those over here. 1, 0, 1, negative 1, 0, 1. Okay, good? Let me circle the things that we've considered here. We've considered x is 0, right? Got it. Lambda is 1 we've considered, yes? Now, we need to look at y is 0, right? Let's just look at it because it's gonna be pretty straightforward what happens. Suppose y is 0. You're going to see we kind of already did it, right? Suppose y is 0. That means equation 2 is good, right? All right, where do you want to go? If y is 0, where would you like me to go now? You want me to go to equation 3 or 1? It's up to you. 3? Okay. So now equation 3 tells you that, what? If y is 0, x has to be 1 or negative 1. We already knew that, right? Okay, and if x is 1 or negative 1, then you can go find lambda, can't you? You can find it where? Where can you find lambda? Equation 1. If you know x is 1 or negative 1, you can go find lambda. So here, so now I'm going to put here, so equation 3 is good. And now equation 1 becomes 2x equals lambda times 2x. Can I divide both sides here by 2x?
No.
Not normally, no, right? Normally, hell no. But what if I just said that x is? 1 or negative 1. So I can divide because it's not going to be 0. Do you see that? So I actually can divide by 2x both here at this point. Or just replace both x's with 1. If you do that, you get lambda's 1. Replace both x's with negative 1, you get lambda's 1 as well. Either way. The result here is that lambda's 1. So equation 1 is satisfied. You have to remember you're living within some assumptions here, right? I think this is part of what makes Lagrange hard is because when you do this, you have to be clear with, to me, the reader, right? You have to be clear that you're working within a certain set of, right now I'm saying y is 1, and this is what I'm saying. And now I'm saying, okay, x is 2, and this is what I'm saying. And it has to be distinct ideas from one another. Okay, what do these look like? Have we done these? Yeah, 0, 1, 1. Wait, hold on. No, it's different, isn't it?
1, 0, 1, 0.
Oh, 1, 0, yeah, 1, 0. Okay, yeah, it's there. 1, 0, 1, negative 1, 0. Okay, all right, so we've done this. We've done lambda 2? We did? Yeah, you can see it right here. Do y'all see that we've already said what happens when lambda's 2? We know it's this. So going back, a step back, when we had done these two, we had to do these two. This one, when I said y is 0, let's work it out anyway, but do you see that we actually didn't have to because we had y is 0 here already?
Yes.
Okay, that's just, you want to stop when you're done. So we could have stopped after these two. That was just to show you get this, you get what you already knew, right? You get what you already knew. All right, so what is the maximum value of this function? We don't know yet, right? This is why I don't like this. The book does it. I don't like doing this with lambda over here because this lambda has nothing to do with the value of the function at all. Nothing. What we want to do to find the max and min now is evaluate our original function at these x, y's. Okay, so now what is the value of the function at 0, 1? What is the value of the function at 0, negative 1? What's the value of the function at 1, 0? What's the value of the function at negative 1, 0? And hopefully from that we'll have a max and a min.
Are we using the
Original function,
okay.
this function right here. So plug in that, you get 2. You get 2 here, and you get 1, and you get 1, right? So the maximum value of that function is 2, and it happens at 2 different places. And the minimum value of that function is 1, and it happens at 2 different places, which matches what we saw here, right? It matches what we saw. So look, that system of equations was pretty straightforward. I've got 5 minutes. I want us to just look at this problem. We're not going to work it out because we don't need to. This problem is almost the same as the one we just did. Do you see the difference? This one, the constraint was what? The circle, right? This one, the constraint is the disk, which now we want the inside as well, don't we? So what we're going to do is we're going to go along the boundary, which we just did, right? We just did that. And then how do you think we take care of the inside? Critical points. The critical points. So we do the partial, set them equal to 0, and then we'll get an answer. Let's see, can you do those partials equal to 0? Set the partial of this equal to 0. Partial x with respect to x equal to 0, you get 2x. Set it to 0, you get x is partial with respect to y. For y, set it to 0, you get y is 0. 0, 0 is a critical point. Plug 0, 0 into that function. What do you get? 0. Is that, what would that be here? If we plug in 0, 0, we would get what? 0? That would be a minimum, wouldn't it? See, what we're doing now is instead of just looking at, instead of our domain being the entire, just the boundary, we're looking at the entire disk. If we plug the entire disk in, we get that instead of just the boundary that went along the edge, right? And so when we find the points, yes, we found those points through Lagrange, right? But Lagrange doesn't take care of the inside. So we found our critical point of 0, 0, we plugged it in, and we were able to see that point on the bottom, right? That point on the bottom we were able to get. So this is combining Lagrange with the critical point to do something on a closed bounded set. All right, I have 4 minutes. That looks pretty unassuming, doesn't it? All right, let's stop. Let's stop. We're going to come back. Where we're headed, though, is, I mean, the functions get harder, but that's not what makes Lagrange get real bad. What makes Lagrange get real bad is that Lagrange extends past functions of 2 variables. So if you have a function of 3 variables, you have the same idea that the gradient has to be equal to lambda times the gradient of g. Now you have 3 variables. Now you wind up with 4 equations instead of 3. So you wind up with something like, those are all examples we have to do still. But here's the idea: when you have a function of 3 variables equals lambda times gradient of a function of 3 variables, that's going to wind up having 4 equations, 4 unknown, and they're all nonlinear. And so you have to sit there and say, well, what if this is this, then go down that road, and then, okay, well, what if this is this, and go down that road. And it's just pretty exhausting, and the amount of work involved, but it's going to be fun. You're going to enjoy it. Study this weekend, right? I mean, this is your weekend before the big test. This is a big test, right? Next week, Wednesday. Look at those reviews. Okay, are y'all doing a study group or anything? Anyone getting together outside of here? No? Okay, just checking. You have a great weekend. Study hard.